Good day, everyone. So, in today's class, we'll be looking at the topic work, energy, and power. At the end of this lesson, we'll be able to know the definition of work, energy, and power. We're going to know how energy is being transferred and how it affects motion, forces, and the calculation involved. Let's dive into this. So, we're going to start with the first one, that is work. What exactly is work? Work can be said to be done when force is applied to an object and the object moves in the direction of that force. Then you say work is done. So two things are involved here. For you to say you have done work, there must be force, and that force must be applied to an object. That's the first thing. Secondly, when that force is applied to that object, then the object must move. Because when there is force applied, there must be movement. Okay, and when there is movement, definitely a particular distance will be covered. So for example, now look at this man lifting the box up. This box was on the floor before. Okay, then the man applied the force that made it to move from the floor to the level of his hand. Then we say that the man has done work. Okay, what is the unit of work? Work is measured basically in joule. Okay, the unit of work is joule. By the formula, by the definition involving force and distance covered, we can also say it is Newton meter. But the SI unit actually for work is joule. It has the same unit for energy. Okay, so work and energy have the same unit, which is what? Joule. Okay, another thing that is common to work and energy is that they are both scalar quantity, meaning that they only have magnitude but no direction. All right. So the formula for work from the definition, we can easily put it to be product of force and distance. So because we say work is done when there is a force applied to a particular object and the object moves through a distance. So by formula, we can say that work formula will be work then will be equal to force times distance. Okay, that's the formula for work. So this distance is sometimes referred to as displacement. Okay, it's a type of distance in a particular direction. So displacement. So three things are involved in the formula: the work itself, okay, then the force that has been applied, and the distance covered. Sometimes this force can be applied in an angular form. Imagine an object, okay, let's say a toy car. Look at this toy car now. Let me just quickly draw a toy car now. Look at this toy car, okay, maybe that is being bought for a little child to play with. And then the little child decides to tie a rope on this toy car, right? So this is let's assume it's the toy car, right? Now the little child decides to tie a rope at the edge of this toy car and decide to hold it. Let's say this is the hand of the little, this is the rope, and then maybe something like this. This is the child. And we just draw a funny cartoon here, okay? Holding the toy car. Now this child is applying a force in this direction, right? But this vehicle will not go up, it will be going in this direction, right? Okay, now there is an angle between that rope and the ground. That's angle theta. Okay, but definitely, even though the force is applied in this way, the movement will be in this way. So in that case, now work formula will be the force, okay, then plus the theta, okay, the angle, then times the distance. Are you getting me now? So the force now that will make this vehicle to move in the horizontal direction will be F cos theta. where the theta there is the angle between the floor and the rope, and then the distance is between the point where the vehicle is before, where the toy car is before, to where the new position. Okay, so that's it. Okay, that's displacement from here, from this place to this place. So in essence, formula for work could be this. If it could be this one if there is an angle involved, and it could be this one if there is no angle involved. That's the summary of what we are saying. All right. So having said that, now let's go further to talk about the second concept, that is energy. What is energy? Simply put, the common definition is the capacity of a system to do work, or some will say the ability to do work. Okay, so that means work and energy are related, kind of. So where there is energy, work is involved. Like I said before, energy and work are both scalar quantity. That is, they have only magnitude but no direction. Okay, and they are both measured in joules. So those are the two similarities between work and energy. All right. So the formula for energy is the same thing for that of work, the general formula. So I will take you back to the previous slide. So if I'm saying work is equal to force cosine theta times d, I'm also saying the same thing as energy equals to the same formula. Also, this place, energy is also what? Force times displacement. Okay. Now, there is a law that governs the usage of energy, and it's called law of conservation. Okay, law of conservation say that the total energy consumed is constant. Okay, the total energy consumed in a closed system is constant. That means it does not change. That's the law of conservation of energy. Energy cannot be created, not be destroyed, but it can be what? Converted from one form to another in a closed system. In other words, that energy, when you use up energy, let me say, okay, for example, now as I'm talking now, I am producing sound energy. Now this sound energy is coming because I have a chemical energy in my body. That's the food I've eaten, right? Now the food I've eaten is being converted towards sound energy. So it's not as if as I'm burning up the chemical energy, it's just gone. No, it is being converted to sound. That's why I can make sound. But I do not have chemical energy in me. There is no how I will have the energy to generate sound energy. All right. So that's the conservation of energy. Law of conservation of energy. It cannot be destroyed, not be created, but it can be converted from one form to another. All right. Now we have forms of energy. We have the potential energy. Potential energy is energy due to position, okay? And it's classified into two. We have the gravitational potential energy, and we have the elastic potential energy. Now, for the gravitational one, this one is energy due to position above a reference level. Look at this stone here now. The energy of this stone at this height is gravitational potential energy, because by the time it will be falling with what? With an acceleration due to gravity. But it's not the time that an object falls from a particular height downwards. Okay, sometimes it can be an elastic potential energy. That is energy stored when an object is stretched or compressed. So when you compress or stretch an energy, such energy is known as elastic potential energy, not kinetic energy. It's still under potential energy, but elastic potential energy, while this one is gravitational potential energy. So they have different formula. So for gravitational potential energy, it is product of mass acceleration due to gravity, because it is gravitational. So product of mass acceleration due to gravity and the height where the object is. Okay, while that of elastic potential energy is half k s square, where the k is called the force constant and x is the extension. We said energy stored when an object is stretched. So that stretching, the distance covered is the x. Okay, so it's half k s square. Some formula we use it as e. Okay, it could sometimes is written like half k is square, right? It can be expressed like this. You can say that elastic PE is equal to half k e squared. So where the e there is the extension or the compression. All right. So I won't say that. Let's now talk about the other type of energy. It's called the kinetic energy. Please note that kinetic energy and potential energy are both under mechanical energy. They are the two classes of mechanical energy, potential and kinetic energy. So for potential, we have said it is of two types, the gravitational potential energy and the elastic. Now we have the kinetic energy. The kinetic energy is the energy due to motion. When an object is moving, that type of energy is known as what? Kinetic energy. And by formula, we say kinetic energy is equal to half mv squared. Why the m there is the mass of the object that is moving, and the v is the velocity of the object that is moving. Okay, half mv squared. Don't mix it up for, do not mix this formula up for the elastic potential energy, which is half k e squared, okay, or half k squared. They are different. Okay. Now we mentioned um, the law of conservation of energy earlier, okay, that energy cannot be created or not be destroyed, or can be converted from one form to the other. So this is now examples of this conservation of mechanical energy. I've mentioned that mechanical energy are just two, potential and kinetic. Now in a system, in a closed system, these energy are constant. It's either it is the whole energy is converted to only kinetic energy, or it is converted to potential energy, or when you sum it up, is to give the same total. Okay, one example is free fall. When an object is falling from a particular height, we call it free fall. In that case, energy is being converted from potential energy to kinetic energy. So when an object is falling, definitely, falling means that it's moving. It has been converted from potential to kinetic. The same thing for pendulum bulb. A pendulum bulb is one of the apparatus in the laboratory we use in performing mechanisms. Okay, let me just really give you a sketch of a pendulum bulb, how it works. In a pendulum bulb, you have two major things there. The bulb is a very small ball, okay, of this nature. Then a string is tied to it, and then it's now suspended on a rotor stand or a ceiling. Now, by the time you displace this bulb here with a string this way, and you release it, it will swing and go to the other side, and from there it goes to the other side, and it keeps going to and fro, on and on and on and on like that. So as the process continue, when the pendulum bulb get to this point, okay, we say that the potential energy is at the maximum, while the kinetic energy is at the minimum. Okay, why it is at the maximum is because when they move from here up to this point, when they move from here up to this point, let me call this point A, let me call this point B, and this point C. Now, when the object moves from point B to point A, it attains a particular height. This is the level here. When they move from here to here, it covers a particular height here. Okay, a particular height h. And when there is height involved, that means the potential energy is high. So at point A, potential energy is at maximum, kinetic energy is at the what? Minimum. At point B is the reverse case. Potential energy is at minimum here because the height is 0 here, while kinetic energy is at maximum. Then at point C, potential energy become high again, while kinetic energy become minimum. So point A and point C have maximum potential energy and minimum kinetic energy, while point B has maximum kinetic energy and minimum potential energy. The point here is that energy is being converted from one form to the other. The same thing applies to a roller coaster. A roller coaster is that coaster it's not a vehicle, but if you go to a relaxation center, that machine that you climb, okay, it has a seat like this. Let me just give a sketch. Okay, there's a seat on it like that. So everybody stay in their own seat, and it keep rotating, It's called a roller coaster. So it keep moving around and around and around like that. Okay, rotating. So as it's moving, height is being lost and speed is gained. But whether height is lost and speed is gained, the important thing is that when you sum up that energy, it remains the same. When height is being low, that means potential energy is zero. When speed is gained, that kinetic energy is I. Okay. At the point where the height is being gained again, potential energy is I, while the kinetic energy is zero. The point is that energy is being converted from potential energy to kinetic energy. Okay, so that is how the law of conservation of energy operates. Okay, so let's talk about the third terms we have for today, and that's power. Power, in this case, we are looking at mechanical power, okay, because we have other type of power. Okay, now power, okay, is the time rate of doing work or the time rate of energy. Either of them is correct. So power is the time rate of doing work or time rate of energy. So we use power to measure how we work or how energy is being transferred. So by formula, power is work over time. Okay, power is work over time, as you will see in this formula here. So power equals to work over change in time, and the unit of power is watt, where 1 watt equals to 1 joule per second. In other words, another unit for power aside from watt is joule per second. So any of the units are correct. So either you say power is watt, or you say it is what joule per second. So you can say the unit of power is either watt, capital W, or joule per second. Either you write it like this or you write it like this, joule/second. So I want to talk about that. Maybe we'll consider one or two questions and then call it a day. Look at this question here. It says that a 500 kilogram car, all right, so in this case, we are giving the mass of the car, M there, with 500 kilogram, right? Which was initially at rest. Okay, if it's at rest, it means that the initial velocity is zero. That's what it means. Anything that is at rest is not moving, right? So that means it's not moving. U is zero. With an acceleration of 5 meter per second square, that means acceleration there is what? 5 meter per second squared, as given in that question. Its kinetic energy after 4 seconds was, so you have to look for kinetic energy after 4 seconds. We are given time to be 4 seconds. Okay, remember that kinetic energy is equal to half mv squared. Okay, kinetic energy is equal to half mv squared. Now, in this case, we are given mass is there, but we are not given v. So how do we get our v? Because if you don't know your v, there is no way you can solve. There's no way you can solve this problem. Now you have to remember your equation of motion. One of the equation of motion say that v square equal to u square plus 2as. In this case now, we don't have distance. S is distance. We have a is given. U is given, and then we need v. We need v. So v is what we need. So we can't use this because we are not given distance in these parameters. So if you look for the this is the second one. If you go for the first one, which is v equal to u plus 80, this is better because this one we are giving u, which is 0, we are giving a, and we are giving t. So we can easily use this to get our v. That v here will now be u is 0, 0 plus our a is 5, and 5 times our t is 4. And that is summing it up. I will give us 20. Okay, 5 times 4 is 20 plus 0, that's 20 meter per second. So our V is 20 meter per second, and that's what we need for this plate. So to get kinetic energy now, Ke will now be equal to half mv squared, which is equal to half times our m is 500, okay, then times our v, which is 20. So 20 squared means 20 times 20, or 20 squared. Okay, so from here we can easily cancel. 2 here is 1, 2 in 20 is 10. So we have 10 times 20, which is 200. So 200 times 500, okay, 200 times 500. So let's do that together. This is 10. Then we have 40. 500 times 10 is 5,000. Okay. Okay. Now times 20. 5 times 2 is this 5 and this 2. That's 10. Then we have our extra 40. Okay. If you check your calculator, you find out that our answer is 100,000 joule. 100,000 joule, right? Now, if you check your answer here, you will see that they are in standard form. So you have to express your answer in standard form. So 100,000 joule in standard form will be 1.0 times 10 to the power 5. Okay, in standard form. So checking our options here, we have 10 to the power 5. Okay, 10 to the power 5 is also the same thing as that. Okay, so 10 to the power 5 is same thing, is equivalent to 100,000. Okay, so the correct answer is A. The correct answer is A. Now, I will leave number 2 to you to attempt as practice question to see if you could solve that question using the formula for energy. All right. So we're going to be calling it a day. Thank you for listening and have a wonderful day. Bye for now.